Hello everyone, my name is Jez Wells and I'm based in the music department at the University of York. This is a short video to accompany the user documentation for the demonstrator of my interactive reverberation modelling system. I'm just very quickly going to go through an example use of both the Reverb Modeler, the part of the software that creates the model of the impulse response that is analysed, and then we'll move on to the Reverb Interactor, where we can use the features of the model itself to dramatically alter the quality and characteristics of the reverberation. Okay, so having installed the software, I then opened the Reverb Modeler, and the first thing I'm going to do is I'm going to import an impulse response. Now this is just a WAV file, audio file of an impulse response of, say, a room or an instrument. Typically, I would expect this system to be used with impulse responses of rooms. So we move to a folder which has impulse responses in, and this French 18th century salon example is one which I talk about in the documentation, and we can play this impulse response. And the first thing that we do is we trim the impulse response. This automatically removes any silence from the front of the recording. And when we do that, we get an estimate of the reverberation time on the left-hand side and on the right-hand side. Now the impulse response is ready to be analysed and modelled. Now there are various options for this which are explained in the user documentation. The default options with phase interpolation turned on, with the iterative analysis method and the analytic amplitude estimation method without any early reflection separation, that's probably the best set of parameters to start with. And as I say, those are the default. So then we hit the Analyze button and you will get a weight bar, which you can see there. And there is a weight bar for each of the two channels. This is a stereo impulse response. Now the modelling itself does take some time, but it is much faster than existing methods and much less computationally intensive as well. And I've recently done a significant amount of work to speed this up even further. So it's now much faster than you can see in this demonstration in the latest version of the software. Having created the model, we can play it back and we can compare it with the original. And then what we need to do is to save the model. And again, we find a location that we want to save into, and here I'll save it into impulse responses. Here's one I created earlier, but this saves the model as an impulse response model, a .irm file. Okay, so having created our impulse response model, we are now ready to load this into the second part of the software, which is the Reverb Interactor, which allows us to play with the characteristics of the reverberation of the impulse response that we have just modeled. So let's see how that works. We click on Load Impulse Response Model. We navigate to the model that we just created. Okay, having loaded it, we can see the time domain waveform in the top left-hand corner of the screen. In the bottom left-hand corner of the screen, we can see a depiction of where the modes are within the frequency spectrum of the impulse response. And the x-axis, the frequency axis, is logarithmic, and that goes 1, 10, 100, 1000, 10,000 hertz, up to the Nyquist limit of about 22,000 hertz in this case. So we can play the IR, and we can also load up a sound that we are going to play through the impulse response via convolution. So let's find something full and bright. Okay, so we can play that sound. Pretty dry brass recording. And what I'm going to do straight away, just so that we're listening only to the reverberation, not the original dry sound, I'm going to move this dry wet slider to 100% wet. We haven't separated out the early reflections to the late reverberation, so we don't need to adjust this control, and if we did, it wouldn't have any effect. And what we can do is we can then convolve this audio with this impulse response. So here's the impulse response. Here's the audio. And here is the two convolved together. Okay, so now we can look at the individual controls. We can control the reverberation time, we can control the room size, and we can control the modal density. And you might think of that as being connected to the complexity of the geometry of the room as opposed just to its sheer size. Okay, so what I'm going to do is I'm going to show you the power of this modelling system, and we're going to go from what is quite a short impulse response, very short reverberation, and we're going to go completely extreme with it. So I'm going to ask for 20 times the reverberation time. Now, lots of different things update. You can see that there's an updated time domain waveform. This is seconds along here. You can also see that the estimation of the reverberation time, the RT60 for the left and the right channels, has now shot up to well over 1 second, 17.4 seconds in the left channel, 16.7 seconds in the right channel. And here you can see something called computation time. Now, because of the significant overheads that this development environment, MATLAB, places on any of these kinds of tasks, it's important to separate out the actual time taken to recompute the resynthesized impulse response from the time taken for other tasks to happen within this graphical user interface environment in MATLAB. So this reports the raw time taken to actually resynthesize the impulse response, and this is 0.7 seconds. So that's how long it took to compute that. Spend a lot of time trying to get that computation time as low as possible, that resynthesis time as low as possible. Let's audition the impulse response now. Now, I think you can hear that that has plausibly extended the reverberation time. You might think, well, the quality of the reverberation doesn't sound that great, and that's simply because we started with a recording which had been made in a very small room, which means that the way that modes are distributed in frequency is not likely to give rise to a particularly satisfying reverberation when it's heard over an extended time period like that. So we can fix that. So I'm going to increase the room size. Now look at what happens to the position of these modes as I do that. Here we go. I'm going to increase the room size to 4 times. And you can see now that there is a big downward shift in the modes. If you think you haven't seen a downward shift, what you've actually seen is an upwards shift, if you like, of the scale. So this was 1 hertz. Now we've gone much lower than that. And you might think, well, what's the point of modes that are lower than 20 hertz because we can't hear them? And that would be a good point. But the thing to bear in mind is that all of these modes have been shifted down in frequency as well. And that's what happens when you have a larger room. So let's have a listen to the impulse response. By the way, that took 0.7279, 0.73 seconds to compute. Now you can hear something which has much less of that kind of metallic sound that we associate with reverberators that don't have a particularly good modal distribution. So I would say that this is now getting towards being a more satisfying long reverberation. Let's take the modal density and let's push that all the way up to 200. And again, you'll see a difference in the distribution of modes when that is resynthesized. By the way, what's happening over here is just some debugging information, some experimental information for me about how many individual atoms of sound are being used to construct the reverberation, to resynthesize it, and also the contribution they make in terms of the energy of the whole impulse response. So let's have a listen to that. By the way, that took a little longer because we're increasing the number of modes. We're increasing the modal density. So that took just under 1 second to compute. But do bear in mind that this is a stereo impulse response that we are resynthesizing with a length of about 17 seconds. Let's play that. And now we get a much smoother sound, and that's typical of rooms where we have greater geometric complexity, and so we get a greater and a better, more even spread of modes. So let's remind ourselves of what the brass sounds like. And now let's convolve them. So I think you'll agree that that has been quite a transformation which has been applied to this original impulse response. Now, whilst that might be impressive, you might say, well, it's not particularly useful to have a reverberation time of 16 seconds unless you're using it for a very special effect. So let's dial some of this back down again and see what happens with more modest settings. Let's give this a try. Okay, more subtle, and I hope giving you the idea that it really is possible to create an almost infinite variety of sounds from just one input impulse response. And remember that all this is being generated from a resynthesis of an actual impulse response of an actual room. Okay, so more detailed information can be found in the user documentation for the demonstrator. The demonstrator is intended to be just that. It's a demonstration of what this modelling is capable of. There is no save feature. If you want to use this modelling system in anger, then you will need to go along to the NewGen website and order yourself a copy of the Paragon Reverb plugin that is based on this modelling system. Thank you for watching.